Without further ado, our featured speaker today is Dr. Jelani Nelson. Dr. Nelson was born to an Ethiopian mother and an African-American father in Los Angeles, California. And then he grew up in St. Thomas, US Virgin Islands. He studied mathematics and computer science at MIT and remained there to complete his doctoral studies in computer science. After the doctorate, he worked as a postdoctoral scholar at the Mathematical Sciences Research Institute, or MSRI, in Berkeley, California, and then at Princeton University at the Institute for Advanced Study. And note that Albert Einstein was a past faculty member at the Institute for Advanced Study. So you know that he's of great caliber. Dr. Nelson holds 2 patents related to applications of streaming algorithms to network trafficking monitoring applications. He's also the recipient in Office of Naval Research Young Investigator Award in 2015, and also an Alfred P. Sloan Foundation Fellowship in 2017. So as I said, his research focuses on sketching and streaming algorithms for big data and dimensionality reduction techniques for high dimensional data. So what probably makes him most proud, given all of his accolades and research endeavors and awards, I would probably venture, he can correct me, I'm okay with that. I would say is probably being a dad first. Shown on the right-hand side is a picture of him in his home with his daughter at the computer. And also to amplify access to programming and constructing algorithms to youth worldwide. He is the founder of Addis Coder, which is a free intensive 4-week summer program in Addis Ababa, Ethiopia, that introduces high schoolers to programming and algorithms. So without further ado, I introduce Dr. Jelani Nelson, who is going to talk a little bit more about a story of coding, big data, and philanthropy. Dr. Nelson?
Hi, thank you for the introduction. Can you hear me well?
Sure can. And
Let me share my screen.
And I see a poll popped up. So if everybody could just take a moment to look at the poll and submit, that would be great.
All right. So just to let you know, the way my setup is, I can't see anything in the chat while I present. So if there's anything in the chat that you want me to be aware of mid-talk, just feel free to interrupt me. Okay, so I'm going to talk primarily about my research area, algorithms for big data, specifically something called sketching algorithms. And then I'll talk a little bit more about Addis Coder and other activities I've been involved with. So I work in algorithms. I'm a theoretical computer scientist. And one of the types of algorithms I work on are sketching algorithms. So what is sketching? You have some data, you have some data set, and you have a set of possible questions that you would like to ask about the data. And sketching is a method to compress that data into a very small memory footprint representation that still supports answering queries about the data, just given this compressed representation. And sometimes you want to be able to apply sketching across multiple data sets. So I have data, you have data, and we want to compute some function of, say, the aggregate data, or we want to compute some similarity metric between our databases or distance metric between our databases. So with sketching, there's another use of sketching. The idea is, let's say that we want to compute some function on the aggregate data. Rather than me having to send you all my data, I'll just first compress my data locally, and then I'll send you the compression, and then you'll be able to aggregate just based on the compression. Or even better, I'll locally compress, you'll locally compress, and then we'll each send to a third party, and that third party can aggregate the compressions and then compute on the aggregated data. There's also something called streaming algorithms, which I'll talk about as well. And the idea behind streaming is I want to maintain this low memory representation on the fly as data is dynamically updated. So I might change data, insert new data, delete data, modify data, and I should maintain this compression on the fly. So benefits of sketching and streaming: one, it's less storage because these are compressed representations. Also, it could be faster to use sketching methods because since your data now has a smaller memory footprint, you can work with it. You can work with this compressed representation in faster memory, like in your cache, for example. Another is the distributed computation application I mentioned, where I have data, you're somewhere else in the world, and you have your data. rather than having to transmit our entire databases over the wire, over the network, we only have to transmit the compressed representation. So it's more communication efficient. So just so we're all on the same page, I'm going to first give you a very simple sketching and streaming example. Okay, there's nothing interesting here, but just so that we're all speaking the same language. Okay, so let's say, for example, our data is we're Amazon, we're some online vendor. There's a stream of transactions where each transaction has a sales price, and there's only one query that we're interested in answering at any given point in time, which is what were the gross sales for the day. Okay, so this has a very easy algorithm, a streaming algorithm, which is that you just maintain a running sum in memory. So your memory just stores one number, right, which is what were the gross sales so far. And then whenever you see a new transaction, you just take that sales price from the transaction and you add it to your single number that you're maintaining, right? So, right, this is an example where you don't need to remember the entire database. The database is like the sequence of all transactions you had throughout the day. You don't need to remember them all to answer this question. It's enough to just store one single number in memory, which is a running sum. So it's very memory efficient. It's also very fast to update your memory state, your compressed representation. It's also very fast to query it. You just return the number. So you didn't need me to tell you how to maintain a running sum in memory. You already knew that. But I just said this so that to clarify what I meant by sketching and streaming, to give you a concrete example. And the rest of the talk, I'm going to give two examples that are not so simple, and then I'm going to pivot and talk about something else. Okay. So the two algorithmic problems I'm going to talk about are it's called approximate counting, and as well as sampling and graph streaming. And let's start off with the first one, approximate counting. So what is that? So it's a data structural problem. Again, you're maintaining data sorted to queries. So here the problem is very simple to state. It's also a problem that you know how to solve, but I'll show you how to solve it better. So what's the problem? You just want to maintain a counter n subject to three operations. Initialize the counter means set it to 0, increment the counter means add 1 to it, and query the counter means return the value of the counter. So for example, again, you're an online vendor with transactions happening throughout the day. Basically, you want to be able to answer like, how many transactions did I have today? So every time there's a transaction, you add 1. So this also doesn't seem to need much cleverness to solve, right? So, but the goal is going to be to use as little memory as possible. And the straightforward solution, which is the solution that is you just remember n in memory, right? So, okay, so at the beginning, there are 0 transactions for the day. I see another transaction, now there are 1. I see another one, now there are 2, and I just keep incrementing that counter in memory. What's the big deal? This seems really easy. So that straightforward solution, if you think about it, like if the number of transactions for the day grows and becomes large, it becomes a d-digit number, then how much memory are you using? You're using d units of memory to remember this d-digit number, because you have to remember each digit, right? How many digits does n have? Something like log n digits, okay? The logarithm of n digits. So like for example, if the digits are base 10, it has roughly log base 10 of n digits. Base 2, log base 2 of n bits. Okay, but anyway, it's like proportional to log n. But this talk is about doing better, using less memory, compressing. I want to use less than d memory to store a d-digit number. Okay, so can I do better? And if you just ask this question, if you take the question at face value, the answer is no. There is no way to remember a d-digit number using less than d memory. You have to remember each digit. But for an interesting variant of the problem, which is still useful for counting transactions, the answer can be yes. And why is that? So here's a number of transactions I had for the day. Okay, you probably will never actually see this number because it's too big. But let's pretend you had a really, really big number n. Okay, so this number, I promise you, I counted it, or I generated it so that this is true. This number has 728 digits. Okay, so rather than store 728 digits in memory, that would consume about 728 memory, I'll only store 3 digits in memory, namely in my memory, I'll remember 7, 2, 8. That's all I'll remember, okay? Now, given that I remember 7, 2, 8, I still approximately know n, right? I know that the smallest n could possibly be is 1 followed by 727 zeros. I know that the biggest n could possibly be is 728 nines, right? 99999. That's the biggest 728 digit number. So I know some range that n is in, and the gap between the bottom of that range and the top of that range is a factor of 10, which means I know n up to a factor of 10. But also, you might say to me, Jelani, I don't just want to know n up to a factor of 10. I want to know n up to 1% error. Okay. Well, that's fine. 728 is just the number of digits base 10. So that's log base 10 of the number. If you want to know the answer up to 1% error, the right thing to do is to remember log base 1.01 of the number. And it turns out log base 1.01 of the number is 168,463 point something. So what I'll do is I'll drop the point something, and I'll just remember the first part, 168,463. So because I dropped the fractional part, I know that the true value of n, if I just remember the numbers 168,463, I know that the true value of n is between 1.01 to the 168,463 power and 1.01 to the 168,464 power, which means I know the value of n up to an error of about multiplicatively 1.01, which means 1% error. And how much memory am I using? I'm only using 6 digits of memory. So that's great, right? I still know the answer with very high accuracy, and I'm using only 6 units of memory instead of 728 units of memory. Okay, but this is not a solution to the problem that I gave you. And the reason it's not a solution to the problem is, what I'm saying here is, if I give you the number n up front, there is a way to compress it, okay? Namely, take the logarithm base 1.01 of the number, round it to the nearest integer, and remember that. But that's not our setup. In our setup, I don't give you n up front and say compress it. You have to maintain n dynamically as n is being updated, right? So initially n is 0, and then someone says increment n, increment it again, increment again, increment again. You never actually know what the real value of n is. You just have to dynamically update your memory state as n is being updated, right? So you don't get the entire n up front and you need to compress it. You need to dynamically maintain n. But anyway, this is just a proof of concept that, something might be possible. And in fact, something is possible, and there's an algorithm due to Rob Morris. Rob Morris was a cryptographer at Bell Labs for a long time. He was also chief scientist at the National Security Agency in the Computer Security Center. And why did Rob Morris, first of all, want to do better, right? I mean, do numbers really get that big? I rarely see 10-digit numbers, and I definitely never see 50-digit numbers. So I mean, it's log n is already a pretty small number. Like my computer has way more than 50 bits of memory, and so does yours. It has gigabytes of memory. So who cares about reducing from 50 bits to 10 bits? Right. So Rob Morris's original motivation was as follows. So he was working on a spell check program for early Unix distributions. And in his spell check, he would look at a text and he would count trigrams. What is a trigram? He would look at how many AAAs are in the text, how many AABs, AACs, etc. So for example, if you look at this text, the researcher is developing Unix. So there's THE, there's HER, ERE, RES. I'm just basically sliding a 3-character window going from left to right along the text. He would count all the trigrams in the text, and then he would kind of gather statistical information about trigrams in the text and use that to he fed that into some algorithm which then labeled certain words as being likely typos. Okay. Now, how many trigrams are there? Well, it's a sequence of 3 letters. There are 26 letters in the English alphabet. So how many sequences of 3 letters are there? 26 cubed. Okay. And given his computer back in the late 70s when he was doing this work, if he had to have 26 cubed counters, he could only afford 8 bits of memory per counter to store the counters. 8 bits, 2 to the 8, so 8 bits basically lets you count from 0 to 255, because 2 to the 8th power is 256, okay? So he could only count trigrams up to 255, but in the text that he was running his typo code on, there were some trigrams that had a count of much larger than 255. So he couldn't actually afford to store the true trigram counts because he didn't have enough memory. So that's why he developed some kind of compression algorithm, which didn't need to store the exact counters, but could store some compressed representation on the fly and dynamically increment them as his code scanned along the text. So his streaming algorithm basically was he was streaming through the characters in the text that he was running typo on. And his algorithm is a randomized algorithm. We're going to see it soon, but here's a plot. Okay, so how did I create this plot? So I implemented his algorithm, and as I mentioned, it's randomized, which means it makes random decisions, okay, as it runs. And what I did was I gave his algorithm a random number between 50,000 and 100,000, and then 50,000. So if you think about it, 2 to the 7 is 128, and 2 to the 10 is 1,024, which means 2 to the 17 is 1,024 times 128, which is about 130 something thousand. Okay, so 100,000 is roughly 17 bits. 50,000 is roughly 16 bits. So in reality, to count up to these values of n, you would need something like 16 or 17 bits of memory. But I gave his algorithm only 8 bits of memory. And I said, I want you to count, basically think of bits as digits. I want you to count up to a 17-digit number, but I'm only letting you use 8 digits to do it. Okay, so obviously you're not going to be able to store the number exactly. You have to do something clever. Okay, so his clever algorithm is a randomized one, which means, and it has some probability of like giving the wrong answer, or giving a very far answer. Okay, so in this plot, what I did was I ran his algorithm many, many different times. This is an experiment. The experiment is give the algorithm n, or like tell the algorithm to increment n times, and then ask it what was the value of n, and then it's going to give you an answer. Okay, and it's going to give you a random answer because it's a randomized algorithm. And then I do that experiment many, many times. So I pick another number n. I say, okay, now increment n times, count what's the value, and then you're going to give me another answer, and then do it again and again and again. Each time that you give me an answer, I record how far off were you from the true value of n. Were you 10% off? Were you 5% off? Were you 50% off? Okay, and this plot basically, it looks like a solid line, but if you look to the right of the plot, you can tell it's not really a solid line. This plot is actually a bunch of little blue dots plotted over and over, plotted all throughout the picture. Okay, and so for each trial, basically what I did was I said, look, after running all the trials, all the randomized trials, if X% of the time your error was Y% or less, I place one blue dot at the point X comma Y. So if you look at 50 in the X-axis, that's the median. So basically, if you look here, it looks like when X is 50, Y is about 8. So half the time, the error was 8% or less. Okay, the median error was about 8%. Meanwhile, if you go to the other extreme, look at 100%, look at X being 100%, 100% of the time, the error was 50% or less. So in all the runs of this algorithm, the error was never more than 50%. That was lucky. Okay, I mean, in reality, it could be higher, but we just got lucky. Not purely luck, but it's with high probability it's going to have this feature. So it never gave an answer that was more than 50% off, and it usually gave an answer that was only 8% off. Okay, and of course, if you give the algorithm more memory, it has better and better error. So that's all nice. Morris had this application from the 1970s, but you might look at that application and say, well, I don't really remember what computers were like in the 1970s, but I remember they were nowhere near as good as they are now, right? We didn't have gigabytes of RAM on a phone in the 1970s. Okay. So now in 2022, what's the motivation? Is the motivation gone because technology has advanced beyond that? And the answer is no. Actually, people are still using the Morse counter. And the motivation is similar to Morse's motivation. So even with Morse, even in the 70s, Morse had enough, Morse's computer had enough memory to store a single trigram count. The problem is he didn't want to store a single trigram count. He wanted to store 26 cubed trigram counts. Okay, so you want to store a lot of trigram counts. So it's the same problem today. What if you don't just have one counter? Yes, my computer can store log n bits of memory, but I don't just have one counter, I have a lot of counters. So there's a multiplicative overhead where I have to multiply the size of each counter times the number of counters. So it turns out that one place where this gets used in modern day is in databases. So there's a very popular in-memory database that I've highlighted here called Redis. It was even voted most loved database of 2020 on some survey, some popular survey. And it's an in-memory database, so people use it as a cache, okay, to store like frequently queried things. And whenever you have a cache, you need a cache replacement or cache replacement policy, right? So the cache is the very fast memory where you're storing things that are frequently accessed. But then, if you have new things that are starting to get frequently accessed, you want to put them in the cache, but cache is full, so you have to kick someone out of the cache, right? So the question is, who do you kick out? And there are many ways to decide who to kick out. Maybe you've heard of least recently used or FIFO or all these things. One algorithm to decide who to kick out is to kick out the element in the cache that is the least frequently accessed. Okay, but if you're least frequently accessed, then what does that mean to be least frequently accessed? It means you have a counter for that. For each element in the cache, you have an associated counter. Every time you access that element in the cache, you increment the counter. And then you can check frequency of the items by looking at who has the biggest counters. The people who have the smallest counters are the least frequently accessed, so they're good candidates to kick out of the cache and replace with new people. And here I found a talk on YouTube. This is just a screenshot from YouTube of a developer for Redis who mentioned using the Morse counter, this compressed counter, to store all these frequencies for items in Redis, okay, in the cache. Right, so it's still being used today. And actually, Redis is open source. All the code of Redis is on GitHub. So if you want, I did it. You can actually go on the Redis GitHub and like find exactly the part of their code where they're using the Morse counter. And there are some other applications in theoretical computer science. As you can imagine, a counter is a very fundamental thing. So if I have a better counter, I could probably use it for a lot of applications. And in fact, that's true. Let me not go through all of them. Let me just explain the algorithm. So Morse's first idea was to use randomness. Okay, so it says it's a randomized algorithm. So he's not going to store n in memory. He's going to store a different number x. And when you say initialize n to 0, he's going to set x to 0. And whenever a user increments n, he flips a coin. And he increments x only if the coin is heads. Otherwise, he does nothing. And the idea is, look, if this is an unbiased coin, then you expect to get heads 50% of the time. So you're only going to increment x 50% of the time. So in expectation, x is not going to be n. It's going to be 50% of n. It's going to be n over 2. But you don't want to know x. You want to know n. So how do you recover n? You just take x and you double it. Right. So if x is expected to be roughly n over 2, then if you take x and double it, you get roughly n. So you still approximately know n, but you're storing a smaller number now, right? You're not storing n, you're storing x. And x is only half as big, so it takes one less digit. Two downsides. One is you're only saving one digit, okay? And the other downside is the error is really bad for small n. So if you think about it, suppose n only got incremented once. With half probability, you won't increment x, it'll still be 0. With half probability, you will increment x, and it'll be 1. But then you double it. So when you double it, you'll either be doubling 0 or you'll be doubling 1, which means you'll either think n is 0 or 2, when in fact n is 1. So you're off by like 100%, right? No matter which case you're in, you're off by 100%. I want to be off by 1%. So first, let's fix the issue about how do we use less memory? And then let's talk about the error. So well, we're just going to be more conservative about when we increment the counter. So now when a user increments n, we don't increment with probability 1/2, but we increment with probability 1/2 to the x. Namely, we flip x coins and we increment if and only if all x coins are heads. Otherwise, we do nothing. There's a probabilistic analysis you can do, I'm not going to do it today, that shows that what you expect is you expect 2 to the x to be n plus 1, which means if you take 2 to the x and you subtract 1, you expect that to be n. So this gives you an unbiased statistical estimator for n. But since 2 to the x is roughly n, it also means that if you take logarithms of both sides, it means x is roughly log n. Now, how many bits of memory does it take to store a number? Well, to store a number x takes log x bits. So to store x only takes log n bits of memory. So iterated logarithm, which is much better than logarithm. Okay, so this is the memory savings. Okay, so this is much better than saving a single bit. You still have the problem, though, that your error is terrible for small n. And now let me give you the intuition. I'm not going to do the rigorous analysis, but the intuition for how you fix that. So the algorithm that I just described says you increment x with probability 1/2 to the x, which is the same thing as 0.5 to the x. And that has very nice memory consumption. It's very low memory, low space, but it's high variance, so you have high error. On the other extreme, you can increment x with probability 1.0 to the x instead of 0.5 to the x. What does that mean? It means you always increment the counter. That's just counting. That you didn't need me to know that algorithm. That's the algorithm you've always been using since you were a toddler to count. Okay, so deterministic counting. If you're just counting deterministically, there's absolutely no variance, which means you have no error whatsoever, but your memory is much higher. So there's this trade-off. So if you take the base of that exponential and slide it from 0.5 to 1.0, you might conjecture that there's a smooth trade-off here. As I increase the base of the exponential, I'm going to use more and more memory, but I'm going to have less and less variance and have better error. And in fact, that is true. You can do that calculation, and you can show that, for example, if you increment x with probability 0.99 to the x, then you can, an expectation n is roughly this expression that I wrote, 100 times 1.01 to the x minus 1. Specifically, if you think of a as being something very close to 0, a is like 0.1 or 0.01. If you increment with probability 1/1 plus a to the x, which is roughly very close to 1 to the x, it's a little bit less than 1 to the x, you can prove that an expectation 1 plus a to the x, you expect that to be a times n plus 1. So if you take that quantity, 1 plus a to the x, you subtract 1 and you divide by a, you have an unbiased estimator for n. And furthermore, you can prove that the variance smoothly goes to 0 as a goes to 0. In particular, the variance can be written as a times n choose 2. And then you can prove that you can get a better approximation via some probabilistic analysis, which I'm not going to do today. Altogether, if you do that probabilistic analysis using something called Chebyshev's inequality, it's going to say that if you want to know the answer up to 1 plus epsilon error, think epsilon is 0.1, 0.01, and it's a randomized algorithm, you want your failure probability to be at most delta, a Chebyshev analysis, or people call it second moment method, shows that the memory you need is proportional to log n plus log 1 over epsilon plus log 1 over delta bits. In particular, set a to be what I wrote in blue, and you'll get that. Okay. Recently, it was shown by me and watching you that this is not the optimal bound. In fact, you can replace the log 1 over delta times log 1 over delta. Okay, so that's something that we did very recently, and we got very excited. So first, the way we came up with a brand new algorithm. It was not the Morse counter, and it was a simple algorithm. And then we also proved a lower bound. The lower bound says we proved a theorem saying that no algorithm, it doesn't matter what you do, the Morse counter, anything you do, it's kind of like a law of nature or a law of math that it's impossible to use less memory than this. Any algorithm needs at least log n plus log 1 over epsilon plus log 1 over delta bits of memory for this problem. And we got very excited and we thought our algorithm is simple. Let's implement our algorithm. Let's implement the Morse counter and let's compare them empirically. Our algorithm is clearly better according to our theorem. So we've improved this algorithm that's 40 years old. more than 40 years old, and we can tell the Redis people about it, and everyone is going to run our new algorithm, etc. So in the panel, can people unmute and speak? If not, maybe I'll just ask a question. If not, if a dynamic conversation is not possible or poll is not possible, basically I just want to know who thinks that, because, even though our algorithm is theoretically better, maybe due to like asymptotic analysis, option A, our algorithm was actually not better than Morris in practice. Morris was actually better empirically. B, our algorithm was better and we were very happy. Or C, something else happened. So any takers on this?
They can put it in the chat.
Okay.
Somebody said A.
Let me temporarily stop sharing so I can look at the chat. One person said A, one person said C. So A was Morris was better. B was we're better. C is something else happened. Okay, so C. I guess C sounds like the most curious answer to give, right? So like, okay, so for the people who are saying C, something else happened. Like what else could happen? Either we're better or they're better, right? Like what else could it be? Like I showed you that plot, right? I showed you the curve for our algorithm, for the Morris counter. 50% of the time, the error was 8% or less. And then the error was never more than 50%. So, so basically what I did was I implemented our algorithm. I plotted our curve, okay? And then I plotted the Morris curve and I compared the curves, like which curve is lower, right? So was our curve lower? That would be B. Or was the Morris curve lower? That would be A. Or C means, I don't know, something else happened. Which curve was lower? Okay, so let me end the suspense. Okay, someone said my curve was lower, which is B. Our algorithm is better. Someone said lower at some point. C, your curve became higher. So maybe like ours started off lower, but then switched to being higher. They fluctuated. Okay, so let's take a look. I'm going to show you. Okay, so orange is our algorithm and blue is the Morris counter from the 1970s. And you can probably tell the curves are essentially on top of each other. So no one is lower than the other. They're basically the same. So we saw this and we were very confused. At first I thought I accidentally just plotted the same curve twice. And then I looked at the code and I realized, no, I'm not plotting the same curve twice. They actually are the different algorithms. And then what we realized is, hey, if you look at this bound, this memory bound that people had proven for Morris, they proved that, if you set the parameter A as follows in Morris, it'll give this memory and it works. They never proved that you need to set A to be this. Like maybe there's another setting of A that also works that gives less memory, but no one had proven that before. But once we saw this picture, we thought to ourselves, people probably were not correctly analyzing the Morris counter. They were, it was not an incorrect analysis, but it was not a tight analysis. They were sloppy in their analysis of the Morris counter. So then we went back and we reanalyzed the Morris counter itself. We gave a completely different analysis and a different proof. And we had to slightly change the Morris counter. And I'm not going to mention exactly how, but a change that everyone who implements the Morris counter actually already does that change anyway, including Redis. But with that change, we basically proved that the Morris counter is also optimal. The Morris counter also achieves this log whatever delta of our new algorithm. So even though we were so happy that we came with this new algorithm, in reality, our new algorithm is like equivalent to the algorithm that was already there from 40 something years ago. So that was humbling, but still we learned something, or humanity learned something. Okay, so that's one problem and one algorithm. I want to tell you about one more story before I switch to other stuff, which is sampling and graph streaming. So so first I want to talk about large streaming graphs, but first a game. Here's the game. You're holding a basket of fruit that is initially empty. At each time step, I will do one of two things. Either, so you're there holding this basket, right? I will come to you and I will either take a fruit and put it in your basket, or I will reach into your basket and take out a fruit. You see me as I'm doing this. So like I have an orange, you see the orange, you see me put the orange in, you see me take a plum out, okay? You see that. Initially, the basket is empty. Now, even though you're seeing me as I'm doing all this, I don't give you pen and paper. You just kind of have to remember what I'm doing. So like I put in an orange, I take out a plum, blah, blah, blah. Okay, so using bounded memory, your short-term memory, when I say query, you must report one fruit that's still in the basket. Okay, so is it clear? This is basically a memory game. It's perfect information. You see everything that's happening, but it's a memory game. Can you remember what's in the basket when I say query? And when I say query, there might be 100 things in the basket. There might be an apple and an orange and a bunch of other things. You just have to tell me one of them. If you tell me just one thing that's still in the basket, you win the game. So let's play it together. Now the basket is empty, but I insert a strawberry, then a watermelon, a grape, an orange, a peach, a banana, another peach. So that can happen. Now there are 2 peaches in the basket, but I removed a peach, so now there's only 1 peach left. Put in a mango. I removed the second peach. Now there are no peaches left. I put in a pineapple, an apple, a cherry, a blueberry, raspberry, pear, plum, blackberry, kiwi, honeydew, tangerine, lemon, etc. You're seeing everything that's happening. I'm not hiding anything from you. And then I start removing fruits from the basket. And you know what I'm removing because you're seeing it right in front of you, right? And then at some point, I'm going to say query. And when I say query, you have to tell me one fruit that's still in the basket. So again, let's type that in the chat. Does anyone have a guess for what's still in the basket? Pear. Not a pear. There's no pear in the basket right now. Nothing. No, I promise you that the basket is not empty right now. No clue. Kiwi. Okay, so I mean, it's not peach, no. So I mean, it's the kind of thing where it's not, even though like in principle you should know because you saw everything, it's not easy to remember all that, right? Like, you know, we have bounded memories, computers have bounded memories. I mean, a computer can remember that because it has a lot more, you know, better memory than we do, but still, they have their own limits too. So cherry, mango, unfortunately, no. So I promise, there are actually 2 things in the basket right now. There's a plum and a lime. And I even said plum in my example. I said, imagine that I put in an orange and take out a plum. So I primed you, but still, it was still hard. So that's a data structural problem. Basically, sort of ignore this turnstile stream thing, some jargon, but it's a problem, right? So there's a universe of possible items, namely like all fruits that exist on Earth. And then at every time step, I either take some element from the universe, take a fruit and add it to the set, or I remove something from the set. And at query time, you just have to tell me something that's still in the set. So it turns out that this is not just a game, but it's real life. Guhan McGregor showed that if you have a data structure, an algorithm that can solve that problem, the fruit game problem, you can use it as a subroutine to find a spanning forest in a dynamic graph. So what do I mean by dynamic graph? Imagine like Facebook, okay? So at the beginning of Facebook, no one was friends with anyone, but then the graph is dynamically changing. Users are getting added. Users are friending each other, right? So if I become your friend on Facebook, that's a new edge that got added in the graph. Or, you know, some people who are dating, like, you know, they broke up and then they unfriended the other person or something, right? Edges can also get deleted from the graph, okay? So there's a dynamically changing graph. Let's say it has V vertices in the graph, V people on Facebook, which is in Facebook is probably over 1 billion people. And you want to know like who's connected to who, not just like direct edges, but is there a path, right? So for example, okay, so I happen to be Facebook friends with Dr. Washington, but let's say that I wasn't, but she's my friend's friend. I want to find that out. I want to find a path to get to her through my own friend network. And maybe she's not my friend's friend. Maybe she's my friend's friend's friend, right? So basically, given a graph that's dynamically evolving, how can I discover all, you know, who's connected to who using a small memory algorithm? It turns out that there is a V log cube V memory algorithm that does this using the fruit game problem as a subroutine. And several other works. So you could say like, what if I don't just, you know, what if I add a twist to the fruit game problem? I don't just want you to tell me any fruit that's in the basket. I want you to tell me a random fruit in the basket. Like pick a uniformly random fruit from all the fruits that are still in the basket. That's a sampling problem, okay? Sampling randomly from a set. And it turns out that there are algorithms for that too, and you can also use those for applications and get low memory solutions for those applications as well. And you might not know what all these different problems mean, but these are various graph problems. Like what I talked about was finding paths to people in graphs, but there are other things you might want to do in graphs, like find dense subgraphs, or finding cycles or minimum spanning trees, or testing, is the graph k-connected, is it bipartite? Find a minimum vertex cover, blah, blah, blah. Okay? And it turns out that for all these problems that I listed here, you can use the fruit game or variants of the fruit game as a subroutine to get memory efficient algorithms for these problems. So now the question is, like, what memory is actually needed to solve the fruit game problem? And the fruit here, I should have, my apologies for using this jargon. Finding an element of support Z in turnstile streams. Okay, I just meant solving the fruit game. Okay, so any algorithm that solves the fruit game, a randomized algorithm. So when I say a randomized algorithm, there's some probability that your algorithm will get it wrong. It'll say the wrong fruit. But with probability 1 minus delta, it'll say a correct fruit. So delta is a parameter you can set. It's like the confidence that you want to have in the correctness of your answer. So if the universe is of size n, there are n species of fruit that exist on Earth. We show that any algorithm needs to use something like log 1 over delta times log squared n bits of memory. And furthermore, it's known that there is an algorithm achieving this. Namely, there's an algorithm by Johari, Sagom, and Tardos that actually achieves this. And we get the lower bounds from something called communication complexity. And we show that the optimal communication complexity for a certain communication game is exactly as I said. And from that, we can derive a lower bound on the memory of any algorithm that processes fruits on the fly and then has to spit out a correct fruit. So I think that's going to be a little too technical, and I don't have that much time left. So let me skip how we actually mathematically prove this and move into another topic, which is evangelism, namely spreading the computer science gospel to all corners of the earth. Okay, so this is something that Dr. Washington mentioned, my work with OddDecoder and other things as well. So before I talk about OddDecoder, I want to bring something to your attention, which actually shocked me. So let's put it in the chat. Who's heard of the IMO, International Math Olympiad? Have people heard of that? Say yes or no. Yes, no, yes, no. Okay, so it's a mixed bag. So if people aren't aware, it's a math contest. Okay, and it's international, as the name suggests. Every country is allowed to pick 6 of the top high schoolers in math across the whole country to represent the country in an international math competition. It's like math counts. So people have heard of math counts in middle school in the United States. Imagine like math counts, but it's a team contest and it's international. Okay. So for example, America has to pick the top 6 high schoolers in math across America. China picks the top 6 in China. Egypt picks the top 6 in Egypt, et cetera. They all go and they take this exam and they look at who gets the best scores. And the problems, of course, have to be quite hard because you're testing the top people in the world, the top kids in the world. So, if you make it too easy, they're all going to get perfect scores. Okay, and most people don't get perfect scores. Usually in any given year, maybe a couple people in the world will get a perfect score, or no people. Now, there's also such a contest for computer science. Okay, instead of a team of 6, it's a team of 4. It's called the IOI, the International Olympiad for Informatics. And again, America picks 4 high schoolers across the country every year. So do many other countries, and then they send them to the world finals and compete live with algorithmic questions. They give them algorithmic programming challenges. So they have like the really tough algorithmic problem, and they have to implement code that solves it. Okay, so in summer 2020, I was invited as a guest speaker to the USA IOI training camp. So the way you get on the American team, Okay, this might not be, people, if you haven't heard of IMO, you probably haven't heard of IOI, I'm guessing, because IOI is like less popular, but it exists. How do you get on the team? How do you be one of the 6 in the math contest? How do you be one of the 4 in the computer science contest? So in the computer science contest, there's a sequence of online contests. Anyone in their own house can go on their computer and compete online, any high schooler. And if you do well enough in the online contest, you get invited to a summer camp at Clemson in South Carolina. It's run by a professor there named Brian Dean. And at the summer camp, it's called USACO Summer Camp. USACO stands for USA Computing Olympiad. And there's like maybe like 25-ish kids who get invited every summer. They train them, they give them a lot of, they give them a lot of lectures and practice problems. And then they run contests there at Clemson. And then they see who are the 4 best competitors, the 4 best performers, in that summer camp. That's going to be the team. Okay. So, it's very hard to make the team. You have to be one of the top 4. Yeah, I'm wrapping up. So, okay, so I was curious, where are these kids coming from? Okay. And I made a heat map because it's all public. You can go on their website and see what high schools do these kids come from. I made a heat map, and guess what? It's extremely skewed. So there are about 150 unique kids who made it to the camp in a decade. In that decade, 60 came from California, followed by 16 from Virginia, followed by 12 from Texas, followed by 7 from Massachusetts. Those are the top 4 states. Notice California is like way more. And where's New York? New York only had 2 kids in a decade compared to 60 from California. Of the 16 Virginians, all but 1 were from the same high school. From the 60 Californians, 57 out of 60 were from the Bay Area, and all but 1 of those 57 were from the South Bay, namely a very small radius around Silicon Valley, like Stanford, Mountain View, etc., Palo Alto. Almost half the states had no participants in a decade. So I looked at this and I was like, wow, I don't think that all the smart kids in America live next to Stanford. Okay. I'm not talking about, these are not kids who are going to Stanford. These are high schoolers who live around Stanford. And what I realized is there are after-school summer camps in Palo Alto, in that area, in Cupertino, where parents can pay to have their kids basically be trained by former Olympians, okay, for this contest. So it's just access to quality training, right? Was creating a differential in outcomes for people. And so I only discovered this recently, but I'm very motivated by identifying like gaps in access to kind of advanced high quality training like this. And I myself, more than a decade ago, launched a summer camp in Ethiopia, where every summer me and other instructors I recruit go to Addis Ababa, Ethiopia, and train high schoolers and provide them with algorithmic training in high school, which is like college level material. And our students have done very well over the years. Some of them, the ones in red, have matriculated into PhD programs. Actually, Jonathan at the top finished his math PhD at RPI recently, and he's now a postdoc in math at, I think, University of Alberta or Calgary. He's in Canada. And we've had a bunch of students also decide to do undergrad in the US, 4 to Harvard, 5 to MIT, 3 to Princeton, et cetera, et cetera, et cetera. So I think I'm gonna wrap it up. Just some highlights. We did surveys. The number of students who went through our program and said, hey, like I didn't want to, basically look at how many students in our program wanted to do CS before the program versus how many of our students wanted to do CS after the program. That number more than tripled. CS is not part of the standard curriculum in Ethiopia. So many of them had no idea what CS was. All the smart students there want to do medicine, maybe engineering. But after being exposed to high-level computer science, they thought this is really cool, and it inspired a lot of them to want to do computer science. We've had our TAs and alums create spin-off programs in other Ethiopian cities. I'm in the process of myself creating a new program modeled on this syllabus in Jamaica. That's going to be hopefully soon a pan-Caribbean program every summer. And some pictures. We're out of time. This is the TAs having fun. The TAs are from all over the place, from Ethiopia as well as from abroad. And there's some Ethiopian food. Okay, so that's all I have for you, and I think I'm out of time, so I'm happy to take questions if we have time for that.
Great. Thank you so much for that delightful presentation, Dr. Nelson. Right now, Bettina has some results from the polls, and if somebody has some questions, we may just go over a little bit today, but I hope that's okay, and that's all good by me. So please put them in the Q&A if you have any questions, but for right now, Bettina will share the results from our poll.
Hi, everyone. Good afternoon. So thank you for joining us for our first data science seminar series of 2022. And it's very exciting to see that we have 44 people that participated. We're up to 47 now, actually, but of those 44, 100 participated in our poll. So just taking a look at who's in the audience, we have 23% or 10 people who are currently enrolled students, and the mass majority, 77%, are graduated or working professionals. For those that are students, we have a few from each student level, with the most coming in at the PhD level with 5. But again, most of the folks here are not currently enrolled. Then looking at gender, we have a pretty even gender split, which I think is probably one of the first times where it's been this close, with 45 and 55%. Where do you currently live? The majority live outside of Georgia. So if you're from somewhere outside Georgia, please drop in the chat your city and state so we can give you a shout out and see how far our seminars are going. And then what level of coding skills do you have, if any? We have 14 people that say advanced, 20 that say basic, and then 10 that say that they're interested in learning or taking data science initiative workshops in coding. So glad to have you all here. How did you find out about the seminar today? 12 found out from our newsletter, 3 from social media, 2 from the speaker himself, and then from word of mouth or email, we have 27, which was 61%. And then for question number 7, are you interested in being involved with the IDIS Coder program by Dr. Nelson? We have 13 who said absolutely, so we'll be looking to connect you with him. And then we have the rest saying that they'll take a look at the website to learn more. And I see in the chat that we have folks from Fayetteville, North Carolina, Syracuse, New York, Charlotte, North Carolina, Berkeley, California, Philadelphia, St. Louis, US Virgin Islands as well. So that's, I think, our furthest one. Thank you all for being here.
Awesome. Thank you so much for that report out of the poll. Yes, and thank you all for being here. If anybody has any questions, you can put them in the chat. And somebody made a comment that opportunity is not equal. So Dr. Nelson, how do you see yourself basically challenging that? So to bring some equity for opportunities for others in this important field.
Yeah, I mean, as I mentioned with like the IOI, I mean, to me, that was the craziest example, which is, I mean, it's actually, surprisingly, it's even gotten a little bit better than it used to be, and I remember when I was in college, like it seemed every year half the team was from Thomas Jefferson High School of Science and Technology in Virginia, right? Which is, not even just one state, but like one high school. It was just about like exposure, right? And access to information. And I think to me, what it shows is that there are a lot of people who just don't have that access, right? So I'm hoping that will improve. And, I'm looking at ways that I can improve it through this program. Also, Professor Mark Boumediene, who mentioned it in the chat, what about the Virgin Islands? I want to give a shout out to him too, because I actually ran an edition of a compressed version of the IDIS Coder syllabus at UVI, University of the Virgin Islands, one time. I think that was January 2015. And he was my host for that, and I want to thank you very much for that. And we're planning to actually, does anyone listen to reggae music? Anyone know Chronix, the reggae singer? No, you do? Oh, okay. I got this surprising email out of the blue like a year ago from the Chronix team saying, we heard about your Ethiopia program. We would really love for you to host something like that in Jamaica. And we'll provide funding for it. So that's happening. And this summer, we're actually going to launch a version at UE, University of West Indies in Kingston, Jamaica. And this summer, it's going to be just in Jamaica, but I'm hoping, in the near future, we'll be able to expand it and make it like a pan-Caribbean, maybe expand further, expand the program to have more students. But yeah, I mean, I think there is an access to information / exposure problem, and we need to do more to, I think, democratize that access.
Awesome. And the words of one of the participants, totally amazing. We really appreciate all your works, both on the research side and also making sure that other people have access to this. So your efforts to really amplify what you're doing to the broader community are, yeah, we really applaud you in all of that. So, I think we've come here at the close of the hour. Thank you, Dr. Nelson, for this engaging presentation. We really enjoyed it. And as somebody asked if this will be available later, yes, it will be available on our YouTube, and we also stream live on Facebook. So feel free to check it out. And we will be back on February 11th at 12 noon Eastern with another seminar. Thanks again, Dr. Nelson, for hanging out with us today.
Thanks for hosting me.